Today we are going to talk about another type of numerical analysis of the Koopman operator method, the finite section method. I'm going to spend a couple of lectures on this topic. So we're going to start with considering the Koopman operator acting on an observable space F of functions on the state space M. And we are going to assume we have a complex inner product denoted as this on it. So to start with, we'll talk about the situation in which we have an orthonormal basis on our space of functions F. So these Fj, j element of n, so positive integers and 0, is an orthonormal basis. And so for any function f, we will assume we have a possibility to expand this function f into the sum of basis functions multiplied with some coefficients. And in this case, the coefficients themselves, the CJs, are really obtained as an inner product between f and fj. So if we take an inner product of f with fj, because all of the fj's are orthonormal indeed, we get j coefficient to be just inner product between f and fj. And now we're going to let ukj, you can think this as an element of a matrix, although it's going to be infinite dimensional, with kth row and jth column, to be the inner product between the action of u on fj and the kth basis function. Then if I wanted to obtain the uf, so that's the next iterate of the value of f under the action of the map T, so represented as the action of the Koopman operator on f itself. If I wanted to get the Kth coefficient, so the equivalent of this guy here, I would take the inner product between uf and fk, right? And then that's a sum over all j, cj, inner product between ufj and fk. What I've done here is observe the linearity of the Koopman operator and passed it over into the sum. And then since this was defined as, since this here was labeled as ukj, so this inner product is labeled as ukj, I get the sum over all j element of n, ukj cj. So that's nice because it indicates that once we choose this kind of a basis in which we have a nice Fourier type series representation, so fj's can be really any basis functions, but in the case of harmonic functions, that would be a Fourier representation. That's what I'm calling it, kind of in a general sense, a Fourier representation. We see here that the kth element, so the kth coefficient of the iterate of f, is given as a sum, an infinite sum of ukj cj. So to think of it, if you represent the function f using coefficients cj, you get the coefficients at the next step by basically acting with a matrix ukj. It's an infinite matrix, but a matrix nevertheless, acting on the vector of coefficients, again, an infinite vector, cj. So this is the way we kind of break the complexity a little bit of the fact that, of course, this f could be potentially, defined on some continuous space m, let's say, a unit square in R2. Okay, so now we saw that the Koopman operator can be represented as a matrix this way. We talked about it a little bit earlier when we talked about the Karleman linearization. Here is it in more general form. And now we're going to see that this works with non-orthonormal basis as well. So if we have some set of basis functions fj. Very often in the literature, these are called library functions. So we choose some basis functions, but they need to satisfy the property that any function can be represented using some coefficients multiplied by the basis functions themselves. So if we act with u on one of such basis functions, again, not non-orthogonal, we can represent it as a sum of some coefficient ukj. Yeah, we're going to label it as ukj, name it ukj, fk. So this is just the kth coefficient in the expansion of fj in the basis fk. All right. So acting with the Koopman operator on an arbitrary function f, whose expansion is some j element of n cj fj, u by linearity passes into the sum, acts on the jth basis element, and then we have a double sum, because you're going to replace this with this. We have a double sum over all j and k's, and then we can take the sums out, and we get ukj cj, and that summed over all j times fk in a sum over k. And you see that the kth coefficient of expansion of action of u on f is again given by sum over j element of n ukj cj. All right. So this matrix ukj is the essence of what we are going to try to, or what we are going to talk about in these lectures on numerical analysis and numerical simulation. So, as we said, we have the kth coefficient of action of the Koopman operator on function f to be represented as the sum. So now we'll talk a little bit about projections, because we're going to try to think about how we can approximate this matrix over here. And the key idea here is going to be that we might have some finite dimensional subspace on which we can project the dynamics, and the key property of that subspace that we're at some point going to be interested in is its invariance. If the dynamics within that subspace is invariant, then we get some very nice results. But let's talk a little bit about projection. We have a closed linear subspace of f. You can have many different projections onto it. Let me show you a diagram in 2D. Let's say you just have vectors v1 and v2. Think in terms of a functional space, these would be actually functions. And we wanted to make a projection of an arbitrary vector x on v1. Well, we could have an orthogonal projection that would be straight down here, but we could also have a projection along another vector, right? So that projection would be something like this. It's obtained by taking a parallel line to this vector v2, and the expression for it is besides the vector v1 and v2 that are the basis vectors, and as you can see, they're non-orthogonal here. The whole thing is in 2D. W2 is orthogonal to v1, and w1 is orthogonal to v2. And 2D, it's easily seen that these always exist. And then the way you get this point here, the projection of x on the v1 axis, is by taking an inner product between x and w1 and multiplying it with v1. So that would be one projection. But of course, choosing different v2s would give us different projections. So there is this general notion of a projection. So the span of v1 was a closed linear subspace in 2D, but if you have a closed linear subspace of f, there are many different projections onto it, as I showed you in 2D. So a projection, a general notion of projection, is just it's just a linear operator that satisfies that if you apply it twice, then that's the same as if you apply it once. So if you project X to here and then try to do another projection, well, you're already there on that subspace. So that second projection is basically gives you the same vector again. So P squared is equal to P. And so we can think of this P as a projection along the space I minus PF. This is the set of functions that you obtain by taking arbitrary functions in F and then subtracting the projection that I've just discussed from that function, from any function in this F. So to see that we can think of P as that projection, just take F, apply I minus P to it. So now we are projecting into this space, and then apply P to project it to the linear closed subspace that I talked about. So that is equal to P minus P squared F, and since P is equal to P squared, we get 0. So in other words, any element I minus PF of this calligraphic F has projection 0 to our closed linear subspace. And that's what I mean by saying projection along the space I minus PF. To see it graphically, and this is what we mean. Here is X. That projection is obtained by taking V2 and kind of drawing a line along V2, right? That's the meaning of that notion. So to summarize, a linear operator that satisfies P squared is equal to P is called a projection. The image or the range of such an operator is a linear subspace of the vector space V, because if you take two different vectors that are obtained as projections of F1 and F2, so G1 and G2, then this linear condition is satisfied, right? So C1 P F1 plus C2 P F2 is P of C1 F1 plus C2 F2. And then the kernel of P is given, so the set of all the vectors that map P maps to 0 is given by this I minus PV. So if you take V, and as I did before, apply first I minus P to it and then P, you're gonna get 0. Okay, so now we know about projections. This is an important concept. And so now remember the matrix U that has elements U, K, J. This is the matrix of elements, you know, in the orthogonal case, it was just application of U to the jth basis vector inner producted with the kth basis vector. Right? And here in the non-orthogonal case, UKJ is really obtained by taking U and acting on the jth basis vector, and then finding the coefficient UKJ that is in front of FK. So these are the ways UKJ are defined in orthogonal or orthonormal and non-orthonormal case. So we have this infinite dimensional matrix, and of course, so this represents U tilde, represents the Koopman operator. But of course, in numerical simulations, we can only deal with a finite dimensional section of that matrix. So here is a square finite dimensional section. You go from U11 to U1n, and then UN1 to UNN, and we call this the compression of U tilde. Compression of U tilde at level n. So that compression satisfies, this UN tilde satisfies Pn U tilde Pn. In fact, this is the projection along I minus Pn F. So this Pn is the projection along I minus P and F to the span of the first n basis functions. Yeah, so let's see how that goes. So let's suppose that we have some set of coefficients that denote the coefficients of f in the basis fk. And in this case, I started from 1 to infinity, not from 0 to infinity. And then we project C in this coefficient space. That projection just means that I have 0 coefficients for all the basis functions with the index bigger than n. So n plus 1, n plus 2, and so on. How's that? Well, the idea is that this projection, what it does, it basically renders all the elements of the vector that are in these other directions, right? So not the directions, not the projection subspace. It renders them 0, right? Makes them 0. So all of these coefficients end up being 0 here. So that's the projection. So what happens is Pn takes some set of coefficients, takes it into this finite set of coefficients, and then it zeroes out everything else. And then U tilde, remember that's the big Koopman matrix, that can take that finite set of coefficients and make them non-zero even for these ones, right? Even for these ones. When you act with this big matrix here, out of these whole things, you can't expect necessarily that you're going to get the rest of the coefficients 0. You get something on here, but then you apply Pn again, and you zero that out again. So these coefficients here would be U11, they would turn into U11C1, U12C plus U12C2 plus U1NCN, and then all these other coefficients by this action are going to be 0. And that's precisely what UN tilde does, right? It just takes elements that have 0 as the rest of the coefficients, and it turns them into elements that have 0 as the rest of the coefficients down here in the rest of the matrix. Okay, so this is called the compression, and then this matrix, or a finite section, that these are the nomenclatures for this. So now the key question is going to be, suppose I have a finite dimensional matrix like this. What does this mean with respect to the original infinite dimensional Koopman matrix? And that's not a trivial question. Cutting off at the finite n clearly might introduce a lot of systematic errors that are going to prevent us from analyzing the system just through the fact that we chose some finite dimensional subspace that is not very informative inside this big space of observables. So that's our problem. But in order to solve that problem, we're going to resort again to spectral analysis. We're going to say, okay, one of the things that we're interested in is things like eigenfunctions and eigenvalues. And it's obvious what that means for a finite dimensional matrix, but the issue of what is called the spectrum. So in finite dimensions, the spectrum would be just the eigenvalues themselves. So you always have n eigenvalues for these matrices. In the infinite dimensional case, it gets a little bit more complex. So let's talk about that for a minute. So we're going to talk about the spectrum of infinite dimensional linear operators, because that notion contains more than the notion of eigenvalues. So when we have infinite dimensional operators, unfortunately, there is no such thing as fundamental theorem of algebra. The fundamental theorem of algebra says that when you form the characteristic polynomial of a matrix, which is an n degree of a matrix of size n by n, that's an n degree polynomial, there are n complex or real roots. So you have n eigenvalues, because the roots of the polynomial are in fact the eigenvalues themselves. So the problem with this is that if you have an infinite dimensional matrix, then of course there is no n degree polynomial in principle that you can write down. Of course, your degree n, if you try to attempt this in a naive sense, will go to infinity. So let's go back to this issue of finding eigenvalues for finite dimensional linear operators. And existence of an eigenvalue lambda really means there is a non-zero vector v lambda such that a minus lambda I v lambda is equal to 0. Yeah, and so this can only be if the determinant of a minus lambda I is equal to 0. And so P of lambda, which is the polynomial, n degree polynomial that you obtain by this, tells us, has n and only n zeros that turn into eigenvalues. Now, if you note another thing, I said that would be futile in the case of an infinite dimensional matrix, that approach. But note that if I write this R, this operator R, that depends on the matrix A and lambda itself as A minus lambda I, that's the one that features in this equation. And if I take the inverse of this, that inverse is going to exist for all lambda except those that are the eigenvalues, right? Those are the only ones for which this is not going to exist. In fact, it's going to blow up. Yeah. And so this operator R, and I dropped the notation with A here, was named the resolvent by David Hilbert way back in early 20th century, working on problems related to quantum physics that was utilized a lot in kind of the modern physics of that era. All right. So for an infinite dimensional operator U, cannot use determinant formalism, but we can use this idea that I just gave, and that is that the existence or non-existence or boundedness maybe of that resolvent is something that could tell that we could use to define what do we really mean by spectrum eigenvalues and so on. So that actually is more complicated than just checking that the inverse blows up. So here are the kinds of possibilities. The resolvent set is the set of all the points such that the resolvent exists on a dense subset of V and is a bounded operator. So in finite dimensions, this would be all the points that are not eigenvalues. Now, in infinite case, the point spectrum is the set of points for which R of U and lambda does not exist. I put back this U as a notation, thinking forward that I'm going to use it in the context of the Koopman operator U. So remember, R of U lambda would be U minus lambda I inverse. All right. So that's the point spectrum. And you could say, well, that's the same as what you told us in the finite dimensional case. So this is very similar. R, the resolvent, just doesn't exist. Now, the continuous spectrum is the set of points for which R of U and lambda exists on a dense subset of our function space or vector space, but it's not bounded. Okay, what does this mean? First of all, why a dense subset? Well, in some cases, like if we have spare integrable functions, you might have an operator defined only on smooth functions, for example, a derivative operator, and then it's defined on a dense subset. But not bounded means that as you take a sequence of points on that subset, it can converge to a point, and at the same time, the norm of the resolvent is going to blow up, right? So it's going to go to infinity. So the resolvent exists, but it's not bounded, and then that kind of point is what is called a point in the continuous spectrum. And then we have this residual spectrum, and that's the set of points for which the domain of R u lambda, that's the resolvent, is not dense in your vector V. So this condition here is not satisfied. And so if you take a look at all of these sets, they basically fill the whole complex plane. So there is nothing left. But these three sets here, the P of U, the point spectrum, continuous spectrum, and residual, they give us the spectrum of an infinite dimensional operator. That's kind of the idea of a spectrum of an infinite dimensional operator. So for finite dimensional operators with distinct eigenvalues, there is a decomposition that you can write, which splits the operator into the sum of projections multiplied with the associated eigenvalues. So what this really is if you look back, if you take any vector V and apply the projection, look at the finite dimensional picture that I had before. This projection would give you, the projection is inner product between X and the dual basis vector W1 multiplied by the vector V1. So the projection projects you to this span of V1, and the coefficient here, that in a linear case we call the, an element component of the Koopman mode, is inner product between X and the dual eigenvector. And the same thing in the direction of V2. So the point of Kth decomposition really is that the action can be split, the action of the Koopman operator can be split into its action on different eigenvectors. In this case, V1 and V2 would be eigenvectors. And of course, that produces that lambda in front. That's called the Kth decomposition, right? So in infinite dimensional space, we have point spectrum, continuous spectrum, and a residual spectrum. And what is interesting, and I'm not proving this, I'm just mentioning it, that there is a class of operators called scalar operators, and U, in this case, very similar to the finite dimensional case, can be represented as an integral over the complex plane. Here is the sum over some complex numbers. It's the integral over the complex plane, eigenvalue multiplied with this dE lambda. What is dE lambda? It's an interesting object. It's called the projection valued measure. So for each lambda, this gives you a projection. E lambda gives you a projection. And the domain of this E are measurable subsets of complex plane. So really, E is a mapping that with each subset of the complex plane associates a projection operator. It sounds like a complicated concept, but actually, if you just consider it in the case of eigenvalues, it reduces to something quite simple. For example, if you know that you have a point P on the complex plane, and at that point you have a simple eigenvalue of the operator with the eigenfunction phi p, in that case the projection is just E of P acting on F is C, some constant phi p. So the projection just gives you the eigenfunction itself multiplied by some constant. You can think of it as, hey, how much of f is contained in that eigenfunction phi p. Now, for continuous spectrum, this is a little more complicated because, of course, it's kind of distributed. It's not a single eigenvalue, but intuitively, this is the concept.